Okay, so continuing on with rate of reactions, and in this video we're going to look at some of the different factors that affect the rate of a chemical reaction, so how fast or slow, or the speed of a chemical reaction. These things can be all described using something called collision theory. So collision theory is this neat little theory that lets us predict and explain all the things that can affect the rate of reaction. Let's get into it. Okay, lots of writing on this slide. Sorry, I try to avoid so much writing, but this one just sort of lends itself a little bit to the text. I do really want you to make sure before you watch this video to watch how to speed up chemical reactions and get a date. This is a TED Ed video, I think, and it gives a really good introduction into this concept of collision theory. So if you haven't watched this video yet, please pause this video. I'll put the link up on the Edmodo page. Go and watch this video. We'll get the link from the notes. Then come back and watch the rest of this video. Okay, if you've done that, let's talk about what is collision theory firstly, and then we will talk about how collision theory can be used to explain a lot of the factors that affect the rate of reaction, or at least 5 of those factors. So the rate of a chemical reaction can be explained using the collision theory. The theory is based on the premise that the particles, that's the atoms or molecules or ions, of which the reactants are composed must collide for a reaction to occur. So we can't get a reaction unless 2 of the particles that are going to react bang into each other, which sort of makes sense. Like, for 2 things to form something new, they have to come into contact with each other, so they have to collide. The second part of this is the colliding particles must have sufficient energy to form an activated intermediate complex from which the products can form. The minimum energy required for an activated intermediate complex is referred to as the activation energy. So we just talked about that activation energy before, that energy to get the reaction started. If the 2 particles just collide with very, very little energy, they might just bang into each other and then just sort of bounce off each other without causing any change, i.e. without any new substance forming. For them to have a new substance form, they have to hit each other with enough energy that some bonds get broken, that they can form some new bonds, some new chemical bonds, and form a new compound. So that's what we sort of mean by this activated intermediate complex. They have to bang into each other with enough energy to cause some change, some intermediate complex, cause something to break, so that then something new can form. Collisions in our collision theory are classified as productive collisions, those resulting in the formation of products. So with those where there is enough energy, the activation energy criteria, if you like, is met, so a new substance can form. Or we can get unproductive collisions, which those not resulting in the formation of products. That's where we don't have enough energy to get something formed. So in terms of collision theory, the rate of reaction depends on the magnitude of the activation energy. So if we have a high activation energy, that means that we'll probably get not many productive collisions, because not many particles will have enough energy to have a productive collision. So then we will get basically a low rate, a very slow reaction, because there isn't many products forming. The number, or fancy word for number, frequency of collisions. So the more collisions, the faster the reaction is likely to be. The less collisions, the slower the reaction is likely to be. The energy of the collisions. So if the particles collide with very low energy, there isn't much chance that we will overcome the activation energy, form the activated intermediate complex, get a productive collision to form the products. However, if we have lots and lots of energy, much more chance that all these criteria is met, I won't repeat them, and that we get a productive collision. So hopefully that just seems fairly sensible. The more energy they collide with, the more chance something will change to form a new product. Now the other thing that can affect them is the orientation of colliding particles. So particularly with bigger molecules, if the collision will have to occur in a certain way or a certain shape, so the two things will have to collide with two bits that need to react, if you like, coming into contact with each other to get some sort of change. So if you think particularly about enzymes in biology, and if you haven't done biology, don't stress, but I think most of you guys are doing biology, if the reactants don't come into collide with where the active site is, then that enzyme is unlikely to help them be able to cause change. So that's what we mean by orientation. They've got to collide in a way that lets change happen. Now the rate of reaction will increase if the frequency of collisions is increased. I've really just said this before. The more collisions, the more rate. The energy is increased. I've already said that before. Or if the activation energy is lowered. And I talked about that in the previous video. If we have a lower activation energy, we can get more reactions started, if you like, for less or the same amount of energy. So that will speed up the reaction. It'll be a more efficient process. You can get more done with less energy. So the rates of reaction are affected by changes in a number of factors. And we're going to look at 5 of these factors. And hopefully by now, if you've understood collision theory, this will seem pretty sensible. The concentration of reactants. Reaction rates increase as the concentration of reactants increases. Why is that? Well, you've got more particles. If you've got a higher concentration, there's more particles. If there's more particles, there's more likely to be collisions. If there's more likely to be collisions, there's more likely to be a faster rate. If you go back, I can't go back to that previous video now, but in the previous video I talked about the reason the rate decreased with time. Let me just do a little sketch here. And we had a line going like that. And the reason that you got a greater rate here than up here was here. So this was actually the products line. And we also had on that graph the reactants line. So as we got less and less reactants, there was less chance of a collision. Therefore, the rate decreased. The next thing is temperature. Reaction rate increases as temperature increases. As temperature increases, if you think back to the particle model from, I don't know, I'm doing this with the year 9s at the moment, and I think it's reviewing some of the year 8 science, but as temperature increases, the particles vibrate faster and faster and faster, so they move faster and faster. If they're moving faster, firstly, there's more likely to be more collisions. The faster they're moving, the more distance they're covering, the more likely that will collide. But not only that, those collisions will have more energy because there is more likely, well, if they're moving faster, they'll have more energy. Therefore, there is more chance that they'll be able to be, well, with energy in excess of the activation energy. So there's more chance of enough energy for a productive collision. Pressure of the reaction mixture is another thing, and here when we talk about pressure, we're talking about gases that can affect the rate of the reaction, and pressure is very much just like concentration that we looked at here. If you increase the pressure, you increase the number of particles that are present. The difference between a gas at high pressure and low pressure is there's just more gas particles squeezed in there. If there's more gas particles squeezed in at high pressure, the rate of reaction will increase. So reaction rate increases as pressure increases. That's because more particles, therefore more collisions. So the more particles you have, the more likely you'll get a collision, therefore the more likely that you'll get a faster rate of reaction. Surface area is the next one. Reaction rate increases as surface area of a solid reactant increases. And you might have done this experiment looking at something like tablets that have been crushed up or marble chips that have been crushed up and reacting them with water or acid. And basically, the reason it'll be much faster is that if you have more exposed particles, so when you crush a surface up, when you crush a tablet up, you increase the area that can react. If you think about, in a really simple sense, a tablet that looks like that. So that would sort of represent the area that's available. You sort of got to think about this in 3 dimensions, but if you think about then that gets broken up into lots of little parts, the total area of all those parts once it's broken up and all those sort of other surfaces get exposed is greater. So more exposed particles, therefore more collisions. And finally, a catalyst. Catalysts provide an alternative pathway from products to reactants which lowers the activation energy, therefore there is more likelihood of productive collisions. So hopefully you can remember that diagram from the last video, but if not, just to do a really quick sketch, we had a diagram that looked something like that with the reactants here and the products here, and we have this sort of energy profile, and that might be without the catalyst, and then if we add a catalyst, that gives an alternative pathway. That pathway takes less energy. Remembering energy was on this axis. Therefore, because takes less energy, there's more chance that with the same amount of energy you get a productive collision. So at the same energy there'll be more productive collisions with the alternate pathway. If there's more productive collisions, more products form, you get a faster rate of reaction. So hopefully what I have said and what you've seen in that video there helps you make sense of collision theory and how it explains how we can use collision theory to explain how concentration, temperature, pressure, surface area, and catalysts, including enzymes, because they are a catalyst, affect the rate of reaction. If it hasn't, please sing out, ask questions, and we can look at it some more. Thank you.